Welcome back to Autisticoder. In today's presentation, we're exploring stacks, one of the most versatile data structures in computer science. Stacks are everywhere, from evaluating expressions to solving puzzles. Let's dive in. A stack is one of the simplest yet most powerful data structures. It operates on the last in, first out, or LIFO principle, which means the last item added to the stack is the first one to be removed. Stacks are widely used in solving problems where order matters, like evaluating mathematical expressions, navigating backtracking problems, or managing function calls through the call stack. In this presentation, we'll explore how stacks work and their applications in programming. Stacks are defined by three primary operations that determine how they function. These operations allow us to interact with data in a structured and predictable way. The push operation adds an element to the top of the stack, ensuring new data is added in the correct order. The pop operation removes the top element, making it essential for managing temporary data or reversing order. Finally, the peek or top operation lets us view the top element without removing it, which is useful for inspecting the stack's current state without altering it. Together, these operations maintain the stack's last in, first out property, making them powerful tools for solving complex problems efficiently. Stacks are incredibly versatile and play a key role in solving many real-world problems. They are commonly used to convert mathematical expressions from infix to postfix notation, a process essential for efficient computation. Stacks also shine in backtracking problems, such as solving mazes or finding paths, where the LIFO principle helps us track and revert decisions. Additionally, stacks are vital for tree traversal algorithms, replacing recursion with an iterative approach for better control. They are a cornerstone of undo and redo functionality in applications like text editors, allowing seamless action reversal. Finally, the call stack in programming uses this data structure to manage function calls, ensuring proper execution order and handling of nested calls.
Let's use stacks to solve a tree traversal problem. We'll revisit LeetCode problem number 112, path sum, but this time we'll use stacks explicitly. To recap the problem, we are to determine if there is a root to leaf path in a binary tree where the sum of node values equals a target. This time we'll use stacks to manage nodes and their cumulative sums. Here's the solution to the path sum problem using stacks. Let's take a closer look at the differences between the stack-based solution and the first solution we covered. The first solution uses the call stack automatically by repeatedly using the hasPathSum function, which makes the code simpler to write. However, this approach can lead to stack overflow errors when dealing with very deep trees. On the other hand, the stack-based solution avoids these issues by managing the stack explicitly in the code. This provides more control over the process and is better suited for cases where the tree depth might exceed system limits. Both methods have their strengths, but understanding when to use each one is key to writing effective code. In our next video, we'll dive into recursion, another foundational concept in programming. Recursion is closely tied to stacks, as it relies on the call stack to track function calls. We'll break down how recursion works and explore its applications, setting the stage for solving even more complex problems. Thank you for watching. If you found this helpful, please like, comment, and subscribe to Autisticoder. A small donation through any of the listed applications would also be appreciated. Your support helps me create more content for our community. Let's keep learning and growing together.